Okay, we're going to look into differentiability and continuity. And if you would like to print or use a sheet to follow along to take notes, you can go to this bit.ly link, prove_diff2. I did have another one that was prove_diff, so I had to put the 2 at the end of it. So go there if you want to print a fill in the blanks sheet to follow along. So let's talk about differentiability. And a function f is said to be differentiable at an x coordinate of c if f prime of c exists. So if you can find the derivative and evaluate it at that point, then the function is said to be differentiable. Now that doesn't really tell you a whole lot. So I have my own little definition of differentiability. And for me, a function is differentiable at a point if you can draw a single tangent with a measurable slope on the graph at C. So I'm a very graphical, I'm a very visual person. I like graphs much more than I like algebra type stuff. So that begs the question, what would be a non-differentiable point? If a function can be differentiable, where could it be non-differentiable? So there are 3 such places where a function is non-differentiable. The first one being a corner or a cusp. And so let's look at a graph that contains a corner or a cusp. And this is a shift of the graph x to the 2/3. And if you look at this cusp, any sharp corner in the graph, my idea of differentiability is that you can draw a single tangent with a measurable slope. And if I tried to draw tangents at that little point, yes, I can draw a line that touches the graph at that one point. However, I can draw many lines. It's not a single line. And at a more mathy definition, we are not locally linear. If I zoom in really close to that one point, it doesn't resemble a line, which is really what we're looking for differentiability. That is a point. You cannot draw a single tangent there. It's non-differentiable. So let's look at another one. The next one is any discontinuity. And so I have a graph here of all 3 of the main types of discontinuities. You can see a removable discontinuity, a vertical asymptote, and a jump. And again, the idea of differentiability is that you can zoom in infinitely close to a graph, and at that point, the graph begins to look like a line. Well, I cannot zoom in on a jump discontinuity. It's too far apart. And if you want to think graphically, I also cannot draw a tangent there because do I draw the tangent up here? Do I draw the tangent down here? You cannot draw that tangent. Similarly, we basically have an infinite jump at this infinite discontinuity, the vertical asymptote. You cannot draw a tangent there. And then again, this removable discontinuity, this is the only one that could be a little bit tricky here. You might look at this and think, well, I could eyeball a tangent. It would look something like that. But there's not a point on the graph for the tangent to be touching, and that's one of the requirements. You have to actually be touching, you have to be intersecting the graph with the tangent, and there's not a point there. Also, if you were to zoom in infinitely close at that point, the graph does not look like a line. It's missing. It's an empty spot. You will not see a local linear pattern if you were to zoom in really close. And then the last one, and this one's really rare, but the last point that would be non-differentiable, quit jumping back up, would be a graph that has a vertical tangent. And so this graph right here is a shifting of the graph of the cube root of x. And if you look at this inflection right here, this point where we swap from bending up to bending down, I can draw a tangent there. If you draw a tangent, if you zoom in infinitely close, that will look like a vertical line. And so the tangent is the extension of that vertical appearance. And I can draw a tangent. However, the tangent must have a measurable slope, and the slope of a vertical line is undefined. And if the slope is undefined, and the purpose of a derivative is to find the slope, or one of the purposes of a derivative is to find the slope of the tangent, therefore, my derivative does not exist at that point, and you would be non-differentiable. So there is a visual representation of the 3 types of non-differentiable points. And let's branch this into a more algebraic approach. So one thing to remember with differentiability and continuity is that if a function is differentiable at any given x coordinate, then that function is automatically continuous at that x coordinate. So differentiability does imply continuity, and the contrapositive of that statement is also true. I often hear students guess when I do this live with a real class. I'll say, well, what would the contrapositive be? And I almost always hear someone say, if f is if f is continuous, then f is differentiable. And that is not a true statement. Continuity does not guarantee differentiability, and the counterexamples are a cusp and the vertical tangent. Those are both continuous functions, yet they are not differentiable. The contrapositive is if your function is not continuous, in other words, you have a discontinuity, then you are automatically not differentiable. And again, going back to the visual, that's describing this section right here on number 2. Any discontinuity automatically means not differentiable. So if a function is differentiable, it is continuous. If a function is not continuous, then it's automatically not differentiable at that point. Okay, so our plan, if we want to prove a function is differentiable, if we have an equation and we want to prove differentiability, the first thing we're going to do is prove continuity, because if it's not continuous, we can stop the proof and we automatically know not differentiable. And continuity in calculus is proven by showing that the limit as x approaches c of f of x is equal to f of c. Now, once you have established continuity, we now have to show there's no corner, no cusp, or no vertical tangent. I probably should have that in here as well. But to show that there's no corner, to show there's no cusp, we need to show that there is not an abrupt change in slope by showing this. We do another limit that looks kind of like continuity, but we look at the derivative, and we want to show that the derivative on the left side of c and the derivative on the right side of c both approach the same number, and m must be a real number. And so visually what we're doing here, if we look at, I'm going to draw 2 graphs. I have one that's nice and smooth, and I'm going to draw one that has a corner. If you look at a differentiable function, which some people describe as smooth and continuous, if you look at a differentiable function, the slope on the left side is exactly the same as the slope on the right side. That's what creates that smooth differentiable characteristic. If you look at a corner or a cusp, the slope on the left side is very different than the slope on the right side. And it doesn't even have to be very different. It could be a slight change. It could be a very slight corner like this. Well, I tried to draw one. And any slight corner, any time that your slope is not exactly the same on both sides, you are creating a non-differentiable point. So let's put this into practice. I'm going to do 3, and then there's one more that I'm just going to show you the answer to that you can do on your own. We want to determine if this function is differentiable, and we're looking at x equals 3. And the first step of proving differentiability is to test for continuity. And to test for continuity, we have to show that the limit on the left side of f of 3 equals limit on the right side of 3 is equal to f of 3. And so my left side of 3 is represented by the function x squared. So that will be 3 squared, and that is 9. The right side of 3 is 6x minus 9. So 6 times 3 minus 9 is also equal to 9. And then f of 3, you must write this last part. You have to write f of 3. F of 3 is also 6 times 3 minus 9, which is also 9. Therefore, I know that f is continuous at x equals 3. And once we are continuous, now we have to show that the function is differentiable, or see if the function is differentiable. And so to test for that cusp, we will ultimately need to find the limit from the left side of 3 and the right side of 3 of the derivative, which means we have to find the derivative. And the derivative of a piecewise function is simply differentiating each of the pieces. It's nothing tricky. So the derivative of x squared is 2x, and that's for x is less than 3. The derivative of 6x minus 9 is 6. That is for x is greater than 3. And so to figure out this limit, the left side of 3 for the derivative is 2x. So that'll be 2 times 3, which is 6. The right side of 3 for the derivative is just the constant function 6. And I can see that those are the same. And because those are equal, I now know that f is continuous and differentiable. So f is differentiable at x equals 3. So we have shown differentiability by going through those steps. Let's look at number 2 here. Also looking at x equals 3, we have x squared plus 1 and 5x minus 3. And so let's look here. We need to test for continuity first, which is done by looking at the left and right side of 3 and finding f of 3. And so let's look at this one. The left side of 3 is 3 squared plus 1. 3 squared plus 1, that would be 10. The right side of 3 is the function 5x minus 3, so 5 times 3 minus 3 is 12. And with that, I already know my function is not continuous. Left and right sides of 3 are not equal. I guess since I have this down here, I'll go ahead and say f of 3 is 10, but at that point it's irrelevant. I can say that f is not continuous at x equals 3 because the limit as x approaches 3 from the left of f of x is not equal to the limit as x approaches 3 from the right of f of x. Therefore, because f is not continuous, we already know f is not differentiable at x equals 3. Okay, so I had these boxes right here ready to unveil our magical test for a cusp, but we don't need to do that. We don't need to worry about that. It's irrelevant. Once we have shown discontinuity, irrelevant. I think I'm spelling that right. I don't know. Not necessary. There we go. Necessary. There. All right. So let's look at number 3 really quick. I'm not going to do 3 in detail for you. There is the function. In about 2 or 3 seconds, I'm going to unveil the answer. So if you want to try this one yourself, pause the video, give it a shot, and here comes the answer. Right. Come on, delete. There we go. So there's my work. It turns out that the function is continuous when you do the continuity test. For the cusp test, you find out that the left side of the derivative is approaching 2, the right side is approaching -1. Those are not the same. So we have a continuous function that is not differentiable. And this one, you could also look at it and think this on the left side of 2 is a line with slope 2. On the right side of 2 is a line with slope -1. So you could very quickly graph that in your head and know that we will have a corner. However, if you are asked to prove differentiability, even if you already know the answer, you still need to go through these steps, the formal proof for differentiability. And then that brings us to number 4, which is a bit of a booger because I've changed the wording of this one. And I say to use the definition of the derivative, which has happened before on the AP exam. They have forced you to do this. And when they say use the definition of the derivative or something to those to that effect, what they are forcing you to do is to find the derivative by one of your 2 limit definitions of the derivative. The shortcuts, your power rule, your product rule, your chain rule, your quotient rule, those are no longer options. Now, that doesn't change the beginning of our proof. We still have to show continuity, which has nothing to do with the derivative. We can find continuity by just looking at this. And so I've done that very quickly. Your left side of 2 is 2 times 2 minus 3, which is 1. The right side is 2 minus 1 squared, which is also 1. F of 2 is 1. We have shown continuity. Now for differentiability, I still am going to analyze the slope from the left and the right sides of 2, but I have to do it through one of these 2 limit definitions of the derivative. And if I have the point of differentiability, if I have an x coordinate that I am interested in, I strongly believe the f of x minus f of a over x minus a approach is easier. The one on the right will work. And if you want to try the right side one, do that. That's fine. It will work if you do it correctly. But I like the left side better. So I'm going to go with that. Whoops. I'm going to go with the one on the left. That is my preferred method if I have the x coordinate of that I'm curious about. And I'm going to have to work out both of these limits in detail from the left side of 2 and the right side of 2. And to do this, we will just have to substitute f of x and f of 2, depending on which side. So for the left side, we're looking here. There's my left. So I'm going to rewrite this limit. As x approaches 2 from the left, f of x is 2x minus 3, f of 2. On the left side, if you plug in 2 there, you get 1. This is over the function x minus 2. And then we channel our limiting skills. What approach do you want to use for that? I'm going to choose to combine my numerator. You can factor out a 2, you can cancel, and it works out fairly nicely as a limit. The right side, I'm going to set up also. Limit as x approaches 2 from the right. F of x on the right side is the function x minus 1 squared. F of 2 on the right side is approaching 1, which we already knew, over x minus 2. And for this one, we have a couple of options. To finish this one out. I personally think expanding it's going to be easier. However, you could factor the numerator as a difference of squares where your first term is the quantity x minus 1 squared. I'm going to pause the video and work these out. You should be able to finish these limits on your own. So let me work this, and then we will show what's happening from the left and right sides, and we'll determine if they give us the same answer. If they do, then the function would be differentiable. All right, and here comes my work for these two limits. And I got 2 on both sides of them. Again, I chose to expand the numerator over here, and x minus 1 squared expands to this. And then the 1 subtracted out, I factored the x out. Things worked out very nicely. So the function is continuous. We have shown that the left side and right side limit derivatives do both approach 2. Therefore, f is differentiable at x equals 2. Differentiable at x equals 2. So there is maybe a not so quick rundown on differentiability and how to prove differentiability.